Our goal here in this section is to define a vector field, give some examples of a vector field, and then I put a note to give the terminology to the word field, the mathematical idea, understanding of the word field. Then from there, we will examine what do we mean by a conservative vector field, and is there any curl? Like Brother Lewis has some curl in his hair. Is there any curl in your vector field? Used to be, okay? Curled out, that's right. So we're talking about a curl of a vector field, and what does that mean? And then lastly, divergence. We just touch on the idea of a curl in this section. We just touch on the idea of divergence in this section. Simple mathematical tools. Later on in this chapter, we will devote a section to the divergence that we will call the divergence theorem. Some circles call it Gauss's theorem. He was the one that actually proved it a little bit later on in his life. It was Gauss that when he was around 21 years old, he received his PhD, and his dissertation was the proof. No one else could prove it before. It was interesting because mathematicians before, Leonardo Euler, who was said to be one of the greats, could not prove this particular theorem. Gauss, very young man, around 2021, actually proved it. You've probably heard of it before, the fundamental theorem of algebra, the fundamental theorem of algebra. And, you know, nowadays we talk about algebra and we say, okay, that's easy stuff. Let me tell you, in a very serious sense, the algebra structures not as easy as you think. Gauss later went on to prove the so-called divergence theorem. What are the useful applications for that? Well, when governments and civil engineering study the flow of water in the earth, the flow of water in a system or building, if you will, how that water flows. Is the water contaminated? Can you find a source for the water? Is it a true source? That's all contained within the so-called divergence theorem. In physics, we talk about so-called fluid dynamics. The foundation of it is the divergence theorem. Okay. Yes, sir. So here, the definition of a vector field. You know, I come back and I look at these calculus books and I say, wow, you know, certain definitions are very lame, and which they are. So the definition of a vector field over a plane, region R, is a function, capital F, that assigns a vector, here this capital F, to each point x, y in R. Whether that's a vector field over a plane or a vector field over a solid, here the solid region Q in the space gives to us points x, y, z. So the vector field over the solid region Q in the space takes a function and assigns to this number a vector at the point x, y, z. Here are some examples that you will run into in your engineering career. Here are some examples that you will see in terms of vector fields. They may talk about so-called force fields. These force fields can be fluid. We can talk about fluid flow, heat transfer, or electric so-called force fields. What's the energy produced by such phenomenon? What's the energy produced from the fluid flow? If you get hired as a civil engineer, instructional engineer at TVA, you're concerned about the fluid flow of that water pressure, how significant that is, whether it may be heat transfer or electric force fields. For the electric force fields, very neat application there. We're kind of touching on it a little bit. We don't have too much time in differential equations. You get more into it in electrical engineering, is applying Laplace transforms to be able to find such electric force fields. We talk about velocity as being a so-called field, gravitational fields. Now, here's a statement that I wanted to say, and that is, mathematically speaking, whether it's discrete math or abstract algebra, some circles call it abstract algebra, or they may call it modern algebra. They mean the same thing. Their fields are defined over scalars meaning numbers, having the properties of closure over addition and closure with respect to multiplication. Closure means that if it's over addition, that is that if I have numbers that are said to be alike, when I add them, do I also get an alike property number? So if you talk about, say for example, if you talk about the set of integers, so if I take two integers and add them, do I get another integer? If you do, it's said to be closed with respect to addition. If I take two integers and multiply them, do I get the product? If the product, an integer, is said to be closed with respect to multiplication. Does it keep all of its terms? No matter how you add, do all the things stay in? Or it may be possible you may add and a term may fall out of that particular field. So if you have a term that when you add, it jumps out of that, then you're in trouble. Say, for example, if you were dealing with the set of numbers, let's say positive numbers. And so is it possible that when you add all positive numbers, you get a positive number? And then the mistake that could be is that if you say that down below, you have to have an additive identity or an additive inverse. These are properties that must be within a field. So if you have an additive inverse, the additive inverse means that if I have some element A, then there has to exist negative A, so that when I add A plus a negative A, I get the additive identity, which is 0. But if you talk about the set of all positive numbers, it fails to be a field because for the set of all positive numbers, there does not exist its negative counterpart, because you're only there talking about all positive numbers. So if that be the case, if you talk about the number 5, and so the number 6, the number 7, 8, 9, 10, all positive numbers, do these positive numbers constitute a field? No, because there does not exist. If I have 5, I don't have negative 5 because negative 5 is not positive, it's negative. So the set of numbers that satisfies these properties, commutativity, over addition, and then also multiplication, distributive property, the additive inverse, which is the negative, the additive identity, which is 0, the multiplicative identity, which is 1. So any number times 1 is that number, and then the multiplicative inverse is for numbers. If the number A exists, then 1 over A has to exist. So you call that 1 over A the inverse of the element A. So that whether it's the identity for addition or the identity for multiplication, watch. If I have A plus a negative A, I get the identity 0. If I have A times 1 over A, I get the multiplicative identity 1. So now in linear algebra, we will define and prove vector spaces. And so all fields are said to be vector spaces, but not all vector spaces are fields, because I give the rationale. Fields are defined on numbers, scalars by themselves. So here, fields exist in the space R1. But spaces are defined on sets of numbers that we call today vectors. So we talk about vector field. Now, let's see where we are today. We want to be able to determine whether or not a vector field is conservative. Good. What we do is we say that a vector field, capital F, is called conservative when there exists a potential function, a function that is in hybrid state. There's no energy that exerts it. It needs something to bump into it, to wake it up. And what bumps into it is that gradient that's sitting in the front of it. So the gradient operates on little f, and it tells little f, wake up. Wake up. And when little f wakes up, he wakes up. So here, a vector field, capital F, is conservative when there exists a differentiable function, little f, such that the gradient of little f is equal to capital F. The function f is called the potential function for capital F. So here today, we want to find the conservative vector field for the potential function by finding its gradient. So basically, if I'm given a potential function, can we find the conservative vector field? In other words, can we find capital F? Let's see. So here, we find the partial derivative of f with respect to x. We get 2x and the partial of f with respect to y, we get 4y. So the gradient of f evaluated at the point x comma y is equal to 2xi plus 4yj. This is the so-called conservative vector field. So very simple, very straightforward. Well, here's the thing. And most times you're not given the potential function. Most times you're just given a vector field, and then from the vector field, they ask the question, find the potential function. That's a little bit tricky. So going the other way around is a bit tricky, but I'll show you. Well, you can argue it that to go from little f to capital F, somehow you took partial derivative. So if I'm given capital F to get from capital F to little f, then apparently I should do some type of integration. And that's the idea. Well, why don't you find the conservative vector field for this one? There you're given the potential function. Just find the gradient. So we get the conservative vector field to be 10x plus 3y I plus parentheses 3x plus 2y j. Everybody with me? Okay, good. All right, try this one. Okay, so you did the partial of g with respect to x, and that gave you 2xy times e to the x squared. You did the partial of g with respect to y, that gave you e to the x squared. Then the partial of g with respect to z gave you 1. So the conservative vector field that represents the potential function is 2xy times e to the x squared I plus e to the x squared j plus k. Is everybody good with that? No, those are just individual partial derivatives. Right. You remember the gradient is defined, you find the gradient, this gradient of little g is the partial of little g with respect to x times I, plus the partial of little g with respect to y times j, plus the partial of little g with respect to z times k. Right? That so-called gradient. Yes, oh, I'm sorry. Now, the goal, like I told you, is really being able to find a true potential function. If you're given a vector field, can you find the potential function? That's our goal. It's our goal here, and then it also becomes your goal in differential equations to be able to find. Here we call it a potential function. In differential equations, they call it an exact equation. What makes the differential form exact? Do the same thing, just use different terminology. So there's a test here for conservative vector field. In differential equations, we say that there exists a necessary and sufficient condition for the so-called exactness. Exactness in differential form means the same as conservative for the vector form. So in differential equations, it's called a criterion. Here, it's a test. So this is the test for a conservative vector field. We write the vector field. You can have a vector field, but the vector field may not be conservative. You can have a vector field, but it might not be conservative. It may not conserve its energy. That's okay. We can figure out whether or not it's conservative in the two space, right? For x, y. If it's for the x, y, z space, we can't use this test. We have to use something a little bit more elaborate. But for here, it's very direct. That is that if the vector field, capital F, can be written as capital M-I plus N-J, capital N-J, we take the partial derivative, the partial of n with respect to x. Is it the same as the partial of m with respect to y? If they're the same, the vector field is said to be conservative. Good. So, yes, sir. Yes, sir. Right. When you have a function for three variables and you ask the question, is it conservative, we use the curl. We'll talk about that in just a minute. Use the curl. That curl later on would, if there's fluid flow, when the water is draining, is it draining in some type of cyclic motion? That's important. That's important later on, yeah. Because if it's not curling, that means that some fluid is backed up somewhere. Ooh, got a problem. Yeah. That's right, man. That's right. And let me tell you, if you're building a structure, you don't want that. We had that issue here in this building here when they first built this. I know because I'm on the third floor in the bathroom. Something's not right, man. We got to call the engineer. Y'all didn't do this right. I know, because it's not curling. So we're talking about the curl for x, y, z to be able to test whether or not it's conservative. But here, for the x, y, for the two space, we just use this criterion, this test. So let's take this particular problem. Now let's identify m. M goes with I, and n goes with j. So here, m is equal to x, y squared, and n is x squared y. Take the partial of n with respect to x. So this is 2xy. And we take the partial of m with respect to y. That's 2xy. Here the test says that if the two partials are the same, then capital F is indeed conservative. Right? So if it's conservative, then we make the jump to be able to go to the next step, find the potential function. But for now, we're just testing whether or not a vector field is indeed conservative. So yes, this guy is conservative. You just test those partial derivatives. Make sure you test the partial derivatives in that order. Right? It has to be the partial of n with respect to x, the partial of m with respect to y. It has to be that. You can't do the partial of n with respect to y or the partial of m with respect to x. That's something else. What is that if it's the partial of n with respect to y and the partial of m with respect to x? But that'll give you the divergence. So we're not talking about that for right now. We're talking about conservative vector field. So why don't you figure out if capital F is conservative. I'm going to write that out, however. So this is 1 over x times I minus 1 over y times j. Determine whether this vector field is conservative. Is it conservative? Why do you say no? They are. So the partial of n with respect to x, I get 0, and the partial of m with respect to y, I get 0. This is m, this is n. The partial derivatives are the same. So yes, it is conservative. Now, if it is conservative, we want to take that next step to determine, find the potential function. Here, I've listed the steps that I want you to use to find the potential function. The neat thing about these steps is that, has anyone had or you're taking differential equations? Okay, so, okay, is it right now? Okay. There should have been, you should know this from chapter, I believe, 2 from that book. You deal with the topic called exact equations. And in that, that's the same idea here. If it's written in vector form, we talk about conservative vector space or vector field. But we can take the same vector form and write it in differential form and get terms like dx, dy, that type of thing. For there, we talk about an exact equation, and it's the same idea. My approach is this: finding a potential function for capital F of x, y. Here, we're looking for little f of x, y. So first, determine if the vector field is conservative. We just got through doing that. So we use that criterion. If it's x, y, z, then part 1, when you determine if the vector field is conservative, you have to use the curl. We'll talk about that later. Use this method, named after one of my late professors. Use the Stallworth method to find the so-called potential function. Here's what you do. You're given capital F. You're given this vector field. So I'm going to integrate. And what you do when you integrate, you know the vector field is given in terms of I, j, and k. So there's some function times I, some function times j, some function times k. Replace the I with dx. Replace the j with dy. Replace the k with dz. Okay. If it's dx, then you integrate with respect to x. You treat y and z as constants or coefficients. Basically, that's the reverse of partial derivatives. If it's dy, integrate with respect to y. Treat x and z as constants, coefficients. If it's dz, integrate with respect to z. Treat x and y as constant coefficient. Now, when you do that, you're going to have this overlapping of certain terms it was meant to be. You're going to have some overlap. That overlap, it may be double, it may be triple. If you have overlap, if you have terms that repeat, delete the repeating terms, but keep one of them. So if I keep on seeing xy, xy, and xy, delete 2 of them and keep one of the xy's. Okay. And then whatever other single terms that you have, leave those in that function. Add your constant plus c, you have the potential function. Let's see. So what I just got through saying are these steps down here. The key is replace I with dx, replace j with dy, replace the k. If it is x, y, z, if it's I, j, k, replace the k with dz. Integrate with respect to that term. The other terms you treat as a constant coefficient. Let's see. And again, this is online as well. A students go at least the day before class and take the notes from online and print them out and bring them to class. I'm not talking about nobody. I'm just saying A students. That's what A student. If you want to be an A student, yeah, yes. Well, let's see. Determine whether the vector field is conservative. If it is, find a potential function for the vector field. So this is in xy. So here we have, well, let me just say capital N or capital M to start there. M is equal to x to the third plus e to the y. And then N is equal to x times e to the y minus 6. So I find the partial of N with respect to x. Why do I start with N with the partial derivative? It's just my personal preference, because to me x comes before y. So the partial of N with respect to x is e to the y. And the partial of M with respect to y, look here, that is e to the y. So yes. So if that be the case, then I'm going to apply this Starworth's method. I'm going to integrate that x to the third plus e to the y. It's associated with I. I'm going to replace that with dx. Then plus the integral of x times e to the y minus 6. Here, that's associated with j, so I'm going to just write here dy. So for dx, I'm going to integrate with respect to x. If I see a y or a z, I treat those guys as constants or coefficients. So this becomes x to the fourth over 4 plus x times e to the y. Plus, I move to the second integral. I integrate with respect to y. When I integrate e to the y, the integral of e to the y is just e to the y. So this is times its coefficient, so this is x times e to the y. And then here minus 6 times y. I add a constant. Now I have a repeat. I have some terms that repeat. Well, x e to the y, x e to the y. I'm going to delete 1, keep 1. So the potential function, we started off with capital F, so I write little f of xy, therefore, is equal to x to the fourth over 4 plus x times e to the y minus 6y plus c. Now, you're finished there, but if you just want to check, we take the gradient of little f. Remember, the gradient of little f is supposed to equal to capital F. So if we were checking that, here the partial of little f with respect to x is 4x to the third over 4 plus e to the y. Bless you. Yes, sir. This is x to the third plus e to the y. Partial of f with respect to y, that becomes x times e to the y minus 6. So then here, capital F, which is equal to the gradient of little f, this is the partial of f with respect to x. This is x to the third plus e to the y times I, plus the partial of little f with respect to y. That's x times e to the y minus 6 times j. That should be what we started off with up at the top. That's it. Now, you don't have to check, but I'm just letting you know that what we're doing does make sense. Okay? Well, it's enough of me. I'm talking too much. You do this one. Is it conservative? Huh? What'd you say? Is it conservative? Yes, it is conservative. Right? Both partial derivatives should be 3. All right, let's see. Jackson, you got it? Okay. Let's see if you got this. Donnie, you finished? Okay. Let's see. I have this little f of x, y is equal to 3x, y minus x to the third over 3 plus y squared over 2 plus some constant. Is that what you have? Okay. Good. Good, good. Man, that's what I want to hear. Very good. All right. Let's try this next one. See what you get for that one. What'd you get for the potential function? Anyone? Oh, it's not. So, is the vector field conservative? No, it's not conservative. So there's nothing you can do. Very good. Now, we've only discussed here the potential function or finding the potential function for the xy plane. Now, the next question is to be able to determine whether or not a vector field is conservative, and if it is, find its potential function for the xyz space. For that, we need the curl. Here, the curl is defined as a matrix. It is a 3 by 3 matrix where the first row is the elements I, J, and K, and for linear algebra, they form the basis for the 3 space. So I, J, and K, and then the second here row or operators. An operator by itself is nothing. An operator by itself is nothing. The tools that you have to operate are nothing if I don't have any specimen to operate on. So here, these partial derivatives by themselves are just operators. They're waiting to do something. They want to operate. I want to operate. What do you want to do? I want to take the partial derivative. And that's what they want to do. That third row, M, N, and P, they come from how capital F is defined. Capital F is Mi plus Nj here plus Pk. So this third row would be those functions M, N, and P. When you compute that, and the reason why they have these lines here is that this is actually the determinant for a 3 by 3 matrix. That's all that is. Now, if you remember that, you know, we had matrices back in high school, and so when we got to college, matrices was nothing because we had dealt with it then. He gives the formula for it. This formula here is the same as what's stated here, but this is just the determinant for a 3 by 3 matrix. I will show you how we compute it in just a very easy way, and I'll show you one time and then you'll have it. But what is this curl? What is this curl? Let me note that. The curl denotes the amount of rotation. Here, capital F is something. Well, what is it? It could be fluid flow. It could be the amount of electricity in a force field. So it denotes, in particularly for fluid dynamics, it denotes the amount of rotation of here, capital F, the fluid from a particular source point. Source point would be X, Y, Z. So here, the curl denotes the amount of rotation of F from a source point x, y. See, if the curl is equal to 0, then we say it's irrotational. So let's see. So find the curl of the vector field at the given point. So we say the curl of f at the point, for right now we just say x, y, z, is equal to this determinant. The first row is I, j, and k. The second row is partial with respect to x, partial with respect to y, partial with respect to z. The third row would be the components. So this is x, y, z. Oh, it's pretty neat, x, y, z. For this is M, N, and P. Get my alphabets together. That was always the hardest thing for me, the alphabets. So anyway, then X, Y, Z. Now here's how I do it. I put set of parentheses here for I. This is always negative. Set of parentheses for J, then plus set of parentheses for K. Now to get the ith term, here's what you're going to do. For the ith term, I delete its ith row and ith column, and then it becomes the determinant of the submatrix of these four guys here. And if it's a 2x2 matrix, the determinant is just the crossing, right? The cross, so it's cross product. This times this minus this times that. So let me draw that up. So for the ith term, I'm going to delete the ith row, the ith column. So then this becomes the determinant of the submatrix of these terms. So it becomes this times this minus that operation. So here, this is the partial with respect to y on x, y, z. So this guy wants to operate here. He wants to take the partial of x, y, z with respect to y. That just gives us xz. And then it's minus, and this way is plus, this way is minus. So then it's minus the operation, a partial of z operated on x, y, z. So this is just xy. So now for j, I delete its jth row and jth column. Red. And so then this becomes the submatrix of this guy there minus this operation on that. So this is the partial with respect to x of x, y, z. Well, that's just y, z, then minus the partial of z on x, y, z, the partial of x, y, z with respect to z. That's just x, y. So now we move to the kth term. So if you got it, you're going to delete the kth row and the kth column. Let me erase all this. We got the red, and we'll put this in green.
So for the kth term, we delete its row and column. So this becomes now the determinant of the submatrix of these terms here. So this becomes the partial of xyz with respect to x, that's just yz, then minus the partial of xyz with respect to y, that's just xz. So now we can evaluate the curl at the point 2, 1, 3. So now we can say the curl of f at the point 2, 1, 3 is the first times the last, x times z, so that's 6 minus 2 times 1, I, then minus y times z, that is 3, minus x times y, that's 2j, plus y times z, that's 3, minus x times z, that's 2 times 3 is 6, there at k. And so this curl gives us 4i minus j minus 3k.
You think you got it? Let's see. Try your hand at this one.
That's what I got. Let's see if you get that. Is everybody good? Okay. So, so no break. I guess we'll just keep plowing forward. No. Okay. So one. That's fine. Give you a couple of minutes. You go right ahead. I don't like Mondays for tests. The next test will be Tuesday. I don't like Mondays. Mondays is rough. You know, your weekend is really busy, and weekend ought to be a weekend. You want to get some rest. Sunday ought to be a day of rest. So we're try to we're getting down to the end of this semester, and so we definitely need to cover everything on time. So I think I had in there for Monday for the test, but I will try to. I think Tuesday should be a decent time. I'm only covering 4 sections: 15.1, 15.2, 15.3, and 15.4. 15.1, 15.2. Well, we'll cover 15.1 today. To Thursday, we can cover 15.2 and half of 15.3. Finish 15.3 on Monday, and then 15.4. 15.4 is very short. And what I will do is just give you just the idea for the test. Very straightforward, based on everything that I'm covering here in class. And you should be good to go for Tuesday for the exam. Okay. India, you're like my son when we're traveling and I'm doing all the driving, and so I frequently must stop and visit the rest area frequently. And so when I came up as a boy, when Mama stopped, everybody got out and took a break. And so when I stopped, I think we went to, this wasn't this last trip, I think the trip before we went to Kentucky somewhere. And so I stopped, and it could have been South Alabama, and went to the rest area. And so I asked, everybody need to go. Come on, let's go. And so, so I get back to the truck. My oldest son, he then wants to go to the restaurant. And I said, I thought when I stopped, everybody's supposed to go. Now I'm ready to go. Now I'm ready to get in the truck, drive, and go. Now you want to. And so my wife said, you shouldn't be so hard on him. I said, I'm not being hard on him. I'm just telling him like I'm telling him. When I stopped, go to the restroom. Don't wait till I get back. Now you want to go. And so anyway, India, thank you. I was about to start, and I came back, and then you walked out. You must be kin to my son. Now I'm just teasing. Oh boy. So now, when we stop like that, it used to get to me, but now it's stopped and I go in. Then assuredly, when I come back, he has to get out and go to the. Josh, you know EJ. Yeah, man, that rascal. Oh boy. Okay. So now we have a vector field in the 3 space, and we want to determine whether or not it has a potential function. So first we got to determine whether or not
is conservative, and then from there, if it is, apply the Stallworth's method like we did for the functions with two variables, x, y. Apply this now to x, y, z. The key now to determine whether or not this vector field is conservative, you have to use the curl. We have to use the curl for this. So we compute now the curl for f. Partial with respect to x, partial with respect to y, partial with respect to z. Here we have the function m, 3x squared plus yz, the function n, 3y squared plus xz, and then the function p, 3z squared plus xy. The theorem says that if the curl is equal to 0, then the vector field is said to be conservative. Let me state that here. And f is said to be conservative. So if the curl is equal to 0, then f is said to be conservative. So I'm going to delete, for the first one, delete where I is, delete its row and column. So I have the partial of 3z squared plus xy with respect to y. That just gives me x. And then minus the partial of 3y squared plus xz with respect to z. That's minus x. So now, take the jth term, delete its row and column. So it becomes this guy, the partial of 3z squared plus xy with respect to x. That's just y. Minus the partial of 3x squared plus yz with respect to z. That's y. Then for the kth term, delete its row and column. So it's the partial of 3y squared plus xz with respect to x. That's z. Minus the partial of 3x squared plus yz with respect to y. That's z. We get 0. So if it's 0, then we apply Stallworth's method, like we did before, to find the potential function. So we look up at capital F up here. So we have the integral of 3x squared
plus yz, this is dx, plus the integral of 3y squared plus xz dy, plus the integral of 3z squared plus xy. And that's dz. So first we integrate with respect to x for that first integral. So that gives us here 3x cubed, over 3. Getting too excited. Plus, integrate this with respect to x. This is x, y, z, plus 3y cubed. Integrate the second integral with respect to y, all over 3 plus x, y, z. Plus, integrate that third integral with respect to z. This is 3z cubed all over 3 plus x, y, z, and then plus some constant. So I have 3 terms that's repeating. I'm going to delete 2 of them and just keep 1. We start off with capital F, so we write little f of x, y, z is equal to x cubed plus y cubed plus z cubed plus x, y, z plus some constant. Okay? Everybody good with that? Well, let's see if you got it. Let me give you this one to do. Can I move on to the next slide? First, find the curl. If it's equal to 0, then find the potential function. Yeah, Indy, I see you kind of squinching your eye. It does look, the function looks kind of faded a little bit. Yeah, I do apologize when I'm putting the information together. For some reason, it just comes out like that. Well, you and me both, and so, you know, I'm very particular about making sure that it's clear.
Is it conservative? Yes. Yep. Is that what you got? Am I off somewhere? Okay. Well, let me see. Could have been in my haste. So let's see. So we agree that F is conservative. That is the curl of F is equal to 0. So we have the integral of y squared z cubed dx plus the integral of 2x y z cubed dy plus the integral of 3x y squared z squared dz. So this is x y squared z cubed plus x y squared z cubed plus x y squared z cubed, okay, plus c. I'm off. So little f of x y z, get rid of that one. This is x y squared z cubed plus x y squared z cubed plus c. How about that? So I put my 2 here, should have been on the y and not the x. Are they all the same? Okay, I'm just blind. Yeah, all 3 are the same. That's right. So we just need one. Well, ice cube, this is not a good day. Okay. That's right. They're all the same. Is that better? Okay, good. You got that, Donnie? Okay, well, okay, well, just help me, okay? I appreciate it. All right. Yeah, that's right. All 3 are the same.
So after this, we talk lastly about divergence, and it's very, how you get it is very easy, but what it says is very important. Are you ready? Okay. So here, and just got 5 minutes, and won't take no time for this. The divergence of a vector field. The divergence is simply just straightforward. The partial derivative, if it's m with respect to x, plus the partial derivative of n with respect to y. If it's in the space x, y, z, just becomes directly the partial of m with respect to x, partial of n with respect to y, plus the partial of p with respect to z. This divergence is a scalar. It's a number. It's no longer, it's not a vector anymore. Why isn't it is not a vector? Because it's really the dot product of the gradient operator with the vector field. What is this divergence? Well, if we talk about hydrodynamics in terms of the fluid flow, which is one of the primary sources that we discuss divergence, especially a lot in physics, is that if the divergence is positive, it means that the particular point becomes a source point here, that the fluid is actually flowing from the source, if the divergence is positive. If the divergence is negative, the so-called point becomes here the sink, right? It's receiving the fluid. And it depends on whatever state that you're looking at. All three are important. You may want the particular point to be a source. You may want it to be a sink. Now, the trouble is if it's a source, but it ends up being a sink, or vice versa, you got some issues. If the fluid is supposed to be flowing from, but the fluid is flowing inward, then you got some backup somewhere. That's going to cause a problem. And then it just may be divergence free here, where this point is neither a source nor a sink. Gauss takes this concept of the divergence, and he's able to calculate the energy from the line integral, or that is, he's able to calculate work using the divergence. And how he gets to that is very classic. So find the divergence of a vector field. Again, just very straightforward. Here, the divergence of f at the point x, y, z. Here we take just the partial derivative of, this is m, this is n, this is p. Take the partial of m with respect to x. This is 2 sine x times the derivative of sine cosine x, then plus here the partial of n with respect to y, well, that's 0, plus the partial of p with respect to z. This is 3z squared. So this divergence is just 2 sine x cosine x plus 3z squared. So just straightforward partial derivatives. So nothing cumbersome there. It was 3z squared. Yes, sir. Just two problems left. We just have time just to do this one. Divergence of f at x, y, z. You take the partial here with respect to x. So this becomes 1 over x squared plus y squared times the derivative with respect to x. That's 2x over x squared plus y squared. Then plus the partial derivative of this jth function with respect to y, that's just x. And then the partial derivative of the kth function with respect to z, that's going to give you a 2z all over y squared plus z squared. And then just this last one, if you can do that one.
What is that? Can you find that divergence and then evaluate it at the point? Just got 1 minute. Shouldn't take no more than 1 minute for that.
Yes.
Hmm.
So you should get 11 for that last one. Very good. Thank you. Good. Thank you. Do the homework for this section online. If you have any questions, come back on Thursday and tell me about it. Go ahead and look at the information, my information that I have out there for 15.2 and 15.3. Kind of familiarize yourself with some of those terms so that when you come on Thursday, we can kind of hit it pretty hard. Okay? Thank you.